Okay. Hello, everybody. So we are performing our third lecture on minimal submanifolds today. Let's recall. Just let me know if something is going off, sound or video or screen. Remember, last time we talked about the first variation. We talked about the first variation, which corresponds to the first derivative of area change, so change in area. So we differentiate the area with respect to time, if you want, parameter area or volume in higher dimensions, and we figure out this formula. Divergence, it's going to have divergence of the variational vector field's tangential component plus the mean curvature vector term. All right, so that was our discussion in the previous lecture. So if you want to make a sketch, so N inside M, we had M manifold inside an M manifold, and you vary, and you have this variational vector field, which doesn't at the beginning need to be perpendicular, and that's defined through phi star. We define the coordinates, and we obtained it. And also we defined the minimal submanifold to be the case that mean curvature vector field is 0, so we called it minimal submanifold, but remark that it may not be absolutely minimizing. It is locally minimizing, but absolutely it's critical. And to be understand whether it's globally minimizing, we need to do a little bit more work, and we need to do the second variation. So that's the point we came up. All right. So today our main focus is going to be the second variation, the second derivative. Second variation. For area, or also if it is just not a subsurface but higher dimensional, in general you can say, we call it volume. All right, so to be able, so we said that this is like taking the second derivative. Second derivative of volume, so that this time for the first derivative we made a variation and differentiate along that. So to make the second variation, you need two directional variations. So that what technically that means it's a two parameter family of variations. Okay, so we need a two parameter family of variations to work on. variations of n inside mm. So that's gonna be a map from n times minus epsilon to the ambient manifold, inside which your submanifold lies with, or immersed with the I function, the inclusion type of function I. Here, of course, you also expect that phi P00 should fit with your submanifolds, because it's a variation of that submanifold, and those standard assumptions. And you have x1 till xn coordinates on n, and similarly define we're going to define the variational vector fields and standard coordinate vector fields. So EI, a standard coordinate vector field, is just going to be phi star of partial xi's, and the first variational vector field T is phi star partial T, and second one is the image of partial S, so image in the second direction. Also for sufficiently small TNS, you can describe, you can write the change in the volume, derivative of the volume form at TS is going to be equal to some multiple of dV at 0, 0, and this was, remember, radical determinant, general determinant divided by radical determinant at 0. X, or maybe P or X in the coordinates. Okay, all right. Okay, so we're gonna try to differentiate twice this time. So to be able to do that in this type of computations, last time we saw that we should differentiate the determinant, and also here again we're gonna need that. We're gonna do that and let's again remind that and apply it. So use again, we are going to be use derivative of the determinant. Last time we compute this under normal coordinates. This time we do it more general and then pass to normal coordinates. You can try to do in many different, all different ways. So this is the way we're going to be doing this time. So determinant Gij prime is going to be you can compute this as itself times the inverse matrix. Determinant Gij, so it's determinant Gij times the inverse matrix times the derivative of the metric. So, or trace of the derivative of the metric. You can think it that way as well. Maybe it's, if you more precisely write it down. So that means right. So this prime is in terms of t parameters. So if you want to indicate that one, you can write it this way. So not to make any confusion, so you should be indicating that it is done through the t parameter. So that's what it means. Prime is the simplified version of what this was telling. Also for the second variation, remember you have the s direction as well, so that when you're writing prime, you should be knowing which one you're using. All right. All right. So here, Gij TS is a matrix of functions. Is a matrix of functions. Is a matrix of functions. Okay. All right. So next we would like to differentiate t. We would like to differentiate t. Differentiate j. J because it's the main term in the area or volume form. To do that, you can just, for simplicity, let's differentiate its logarithm. So it's gonna be slightly better for us to write down the denominators. So time t derivative for the logarithm j is gonna be nothing but, remember, nothing but just if you expand inside, this is radical g over radical g0. So like g is gonna denote simply the determinant Gij. Okay, just a notation, simple notation. Similarly g0, and if you start differentiating, then this, of course, the constant term is gonna disappear. So the square roots are gonna come front as 1/2. Logarithm g minus 1/2 logarithm g0, and of course the constant term. This is going to disappear after differentiation. After differentiation, and you're going to have let's see whether we're going to have a room here, and we're going to have the second term drops. Maybe it's going to be like this at the end, and what you have is going to be just the first one, 1/2 partial t log g, and maybe we're going to pass to the next slide, maybe. And that's going to be equal to, it's going to be equal to 1/2 partial tg over g. And if you, so this is where we can plug in the derivative of the determinant. So just write what we have on top here with the adapted notation: g times g inverse matrix times partial t gij, and we have g on the denominator, which cancel out with this. Okay, all right. And you're going to left with a simpler expression, which is just 1/2 gij. Oh, that decided to eat at this time. Okay, gij partial t gij. Okay. Right, that's where that's what we end up with at this time. And then if you want to open this, so we should be, so the inverse matrix stays, so there is a derivative here of the metric, and let's open this up. Open this up. That's gonna be 1/2 gij. Remember, partial t is nothing but capital T, the variational vector field, and gij is ei inner product with ej. So if you write in the, if you turn back to the global expression from local expression with this notation, you can open this up. You can open this up by just using the Leibniz rule. Leibniz rule, 1/2 gij nabla tei ej plus EI nabla TEJ. Okay. And then you can see these two terms very similar to each other. Just I and J are replaced, so that you can make use of the fact that, for example, GIJ for example, GIJ EI nabla TEJ is you can just change GJI because it is symmetric. Remember, metric is symmetric. EI nabla E TEJ, and then you can exchange I and J, and that's going to be GIJ EJ nabla TEI. Okay, from here you can see that these seemingly different, these two terms are going to be the same after contracted with GIJ, so that's going to be you can write it's as twice of the first one, so you can just drop one of them and okay, so let's see, it doesn't disappear. All right, yeah, so maybe I can write it here. This implies that you have GIJ, just the first term is going to be enough. Nabla T EI EJ. All right, so that's how we open up this derivative of the metric part. And if you summarizing, this is not, that's how we find partial J over partial T, and that happened to be partial J over partial T. So this is actually the derivative of the logarithm, remember, so that you have, it is this was equal to, this was partial T log J, which was partial J over partial T, partial J partial T over J, remember, and partial J partial T is going to be just, if you want, you can just indicate the summation that there is Einstein convention actually we are applying, but in the result it's better to put the summations. So far what we proved is this derivative derivative of j, and we haven't yet used any specific coordinates, so this is nothing but happening in general coordinates. Okay. So this was a preparation for the second derivative. Now we can look at the second derivative. Second derivative. So this is actually a mixed partial derivative. That's what we mean, mixed. If you want to think in terms of calculus, this is nothing but mixed partial derivative on manifolds, of course. That's the analogy, but on manifolds, you should be using variational vector fields deformations. All right. So once this time we have partial square j, partial s, partial t, and we would like to look at that at just the starting submanifold over the starting submanifold. What is the second mixed partial derivative? That's what we would like to learn about, and if you write in terms of global notation, this is partial s is the t variational vector field, partial t is the capital T variational vector field. This is nothing but st of j. Applied to j. That's the global notation. Global notation. Global notation. Okay. All right, then we can plug in the preparatory terms we computed, partial j, partial t, right? And this already we computed in the previous stage. So S of summation ij runs from 1 to n. So we are in an n manifold of the inverse metric partial I. I'm going to make an abbreviation that's erasing EI. Instead of EI, I'm going to use I sometimes, so that to make things a little bit faster. So that was nothing but the first derivative, and if you apply S on that, so you should be, so you have three different terms here. Now this is where I'm gonna pass to Einstein convention again. Einstein convention again. Don't want to write the summations at this point, because there is going to be at least 3 of them at each stage. Okay. Einstein convention. Right. Maybe I can keep them. Okay. Let's see. Okay. So let me put them. And okay, you can differentiate one by one. S Gij nabla I T J J plus Gij, the derivative of the second one, nabla I T J J and plus Gij, derivative of the third one. SJ. And now we were in general coordinates till this time. Now pass to the normal coordinates. Pass to the normal coordinates, and remember then in normal coordinates at P00, of course. So here also you have to plug in P00 till the end, at the end. And remember, JP00 is of course, JP00 is of course 1, because those terms are the same. P00 equals 1, so that you can get rid of those. So that those are going to be, these two J's are going to disappear in the next step, because they're going to be 1. They're going to be 1. And we're going to have a more simplified one. Let's write it now. So sum is Gij nabla I T J plus Gij S nabla I T J plus right now. So the first term was ST actually, and the second term is going to be SJ, but SJ is the first one is TJ and second one is SJ, but SJ and TJ only difference is just its name. So that means we have the same term again. All right, so same. We're going to have the same term. And also, oh yeah, right. Remember, okay, okay. Also, like before writing that, so I would like to make this simplification as well, of course. So here also Gij is in normal coordinates. It's going to be equal to 1, right? So that's going to also disappear. So let's not forget about that one, so that we're going to have room here. So the inverse matrix is also at the point P00 with normal coordinates. It's going to be 1, so that term also disappears. So let's make some room for the next term, so to make efficient use of the board. Okay, that's how it is. Okay, now it looks nice. Plus now you can write down now. So here also Gij is going to be becoming 1 and disappearing again. So this one also disappears by multiplying by 1 and partial IT. And also, yeah, right. So right, it becomes they become Kronecker deltas, right? Kronecker deltas, and they disappear, but yeah, they take the trace of what lies in the rest. Okay. All right. So yeah, so let's count their effects. In the rest, okay, so that means you have summation over I here, and here also you have summation over I, because it made the trace effect. And for the second SJ term, so that's nothing but the same for TJ term, so that you can write it as similar to the first term, but you should be using a different index, of course. Okay, use an independent index so that one can understand that it is an independent term. Okay. All right, so we use J for that one, so that separate these two terms from each other. So they are the same term, but with different indices. Okay, so we have a little bit more work to simplify this thing. Actually, we made the almost the hard piece handled. A little bit more effort is gonna give us the answer. So now we have first, second, and third. So we have three different terms. So simplify these three terms is gonna be our next goal. Simplify these three terms. Yeah, to be able to do that, we need to handle the derivative of the inverse matrix. Okay. So derivative of the inverse matrix. Okay, so when you're dealing with differentiation of area and volume, as we see, we come up with the derivative of the determinant often, and also this is the another phenomenon that derivative of the inverse matrix also frequently comes up. So that's the for us that's where that part comes out, so that you should be able to differentiating the inverse metric or matrices as well. Okay. So how to do that? So you should be first use the definition of the inverse matrix. So it is defined to, remember, it has the property that GIK inverse times the matrix should be equal to Kronecker delta, so identity matrix. All right, so that's how the how we define the inverse matrix. So you should, if you differentiate these, if you differentiate both sides, then what you're going to obtain. So differentiate with respect to S is what we're going to be needed. So you also use Einstein convention here. Einstein convention, SGIK times GKJ plus GIK SGKJ equals 0. Put 0 and here SGIK GKJ equals negative of GIK S GKJ So multiply both sides with GJT, both sides, multiply with GJT, so that eventually you should be getting, so you're gonna have Kronecker delta here with changes k's with t's. All right, let me just write it in one more term. So that's gonna amount Kronecker delta kt equals minus GIK S GKJ GJT. So in the right hand side, no simplification. Okay. All right. So this Kronecker delta is, you can think it as GKT as well, no problem. And if you summarize what you did, so this is SGIT. So derivative of the inverse happened to be minus GIK. So inverse matrix times derivative of the metric or matrix times again the inverse matrix again. Okay, so minus inverse derivative inverse, and you just make a change of variables. This is not change of variables, just relabeling. Okay, relabel only to use it in our computation, just to be compatible with what we just started. So here we are trying to simplify the three terms, and this was the discussion related to the first one. So for that one, we need to differentiate the inverse matrix, and that's what we did here, and just transfer this to our variables correctly. So you should change t into j, and j is with else. Okay, so to be compatible with our computation. So minus inverse derivative and inverse again. So that's how is the derivative of the inverse matrix. And then if you look at the normal coordinates, then this is nothing but the Kronecker delta IK is G KL stays, and another Kronecker delta LJ, and finally what you left with is minus SG. Indices are changed to be I and J, and if you want, you can write this as minus S EI inner product with EJ. All right, and if you make this differentiation, minus nabla S, just to remind you, this was nothing but EI EJ minus, again this times EI nabla S EJ, EI EJ. Okay, EI EJ. All right, and then remember, you can exchange these two without any hassle, because since we assume that x1 till xn with new coordinates S and T, variation directions forms a coordinate system, so that Lie brackets among each other are going to be 0, so that you can flip these guys over, and get nabla SEI EJ minus. So you can do it for the first term as well, so that let's do all of them at once. So nabla EI S EJ minus nabla EJ S EI. Okay, just flip both of them to make it ready. Okay, so that's what the first term is going to become, and let's simplify the second term as well. And all right, we're not gonna do something to the third term at the moment, but after we plug in everything, we can do we can simplify that one too. So let's look at the second term, term B, I call it. So that was, remember, S of nabla I T I. That was the term which comes up as the second one in our second variation, and just simplify this to so if you distribute S inside nabla S nabla I T I plus, as you see, this is not local coordinate, this is invariant notation actually, but just abbreviated, so not confused with that one. All right, so you use the Leibniz rule both sides, or product rule for both slots, and here, this, if you, whenever you see something like this, this tells you that there is a curvature terms coming up, and if you can just write down the Riemann curvature tensor instead of that. So RS EI T EI, and but it has a, of course, needs a compensation. One term is missing, so that you can changing S and I is going to give you a curvature plus its reverse, EI plus T and the third term just stays with some small arrangement, so that we want EIs in below, remember, so that this is EI S, how we write it. Okay, so that's the that's how we open up the second term as well. So plugging these in, plugging into the second variation. Plugging into the second variation. Okay, so it seems we managed the hard work done, and so we're just gonna arrange the terms, and we are fine. The hard work is accomplished. And we can now compute the second variation completely as we wanted. Remember, it was partial square t, partial s, partial t. That was the expression we are on to. And plugging A and B, so we had SGIJ, so we have a sum, and SGIJ we already computed to be computed with a negative sign, with a negative sign of, it was, so this summation is over I and J. Nabla EIS EJ EJ plus Nabla EJS EI. So that's what we expanded term. We would like to simplify, but it expanded times. This term was already there, so we just keep it there. So EI TEJ. Okay, so that was the A term plus, let's look at the B term. Plug in the B term, RSEI TEI TEI this one is just running over EI, remember, plus the commutation term EI nabla S TEI, and plus covariant derivative terms for T and S EIS. Okay, so this was the first term, and this was the second term, and the rest term we haven't yet done anything extra on. So that was nabla EIT EI you can just write a square, maybe looks better. All right. Okay, so let's call it C maybe. All right, so this is how the second variation formula. So this is second variation formula. Second variation formula. Famous. And today we devote the time to extract it, and tomorrow in the final lecture we're gonna do some special cases and to how to understand how to understand and make use of this formula. For example, special case here. We're gonna talk about this one as well in detail. Special case here. S, you can take the second variation to be the first one as well. So S equals T, so that also you can look at the normal variations only. That's gonna give us the second derivative of the minimal area actually. So next time we're gonna see the instance of second fundamental form, Ricci curvature, and covariant derivative terms in the expression. To able to interpret this formula and we're gonna talk, and after that we can talk about the stability of minimal submanifolds, which means whether they're actually globally minimizing or not. Right. So next time we're gonna see how we understand and get information out of this second variational formula. All right. So that's all for today. Any questions? Okay, thanks for coming.